This is an annual event. It's an information theory workshop. So, sort of like a structure like a conference, but not really, because most of the stuff that is presented is sort of in progress, new ideas, promising results, or things that people really want a lot of interaction. They want to gin up more support. So, more like a workshop rather than a conference. So, ITA stands for Information Theory and Applications, and the organizers try very hard to balance it between things that are theoretical and things that are they're applied. So application specific, actually get out and do it, have the molecules moving around, stuff going over the air. So the first one I went to, and I'm just going to put it, this is the abstract, and I'll distribute the slides later. So it's a very dense abstract with lots of keywords, and it's about active beam learning for full duplex wireless systems. Okay, so remember, I only have an MSEE here, so I'm going to give the interpretation. This is mainly about MIMO, massive input, massive output antenna arrays. So lots of signals coming in, lots of signals coming out in a complicated array. And we hear about MIMO all the time with cellular. So in-band full duplex can help deliver on the 6G promise. That's the sort of vibe here. That's one of the stipulations. When we talk about in-band full duplex, this is definitely a cellular 6G thing. The downlink and the uplink are at the same time on the same spectrum. And so this sort of looks like our Neptune project of interest to Neptune, which is an OFDM physical layer on the 5 gigahertz band, mainly for drones to kind of challenge the DJI hegemony here. But full duplex in the real world doesn't look like Mathland. So when you do full duplex in MATLAB and simulations, everything's kind of nice and controllable, and you can convince yourself that full duplex works great. But the real world, the signals are completely different. They're kind of nasty. So here in this particular project, we're assuming an analog beamforming kind of situation. And so what do we have to deal with? Well, we have signal noise ratio. We've got massive input, massive output, self-interference channel. We've got TX and RX coupling together, cross-link interference, and all those types of interference is actually mathematically kind of different. Okay, so here we are at the A and the ITA. We're assuming Ricean channels. That's going to be as close as we can get to real channels. Key metric is uplink, downlink spectral interference. And the main idea here with these sorts of channels and these sorts of systems is we need to close the link as fast as possible. We need to figure out like where you are in the footprint of your cell as quickly as possible, close that link as fast as possible. And this kind of speaks to the more general sort of synchronization problem that we have like with opulent voice. Like we're looking at trying to figure out in a coarse sense how fast do we synchronize our signal, how fast do we acquire our signal. Anything that can make it close the link faster is better. So we need to acquire the channel information very quickly. So if you're familiar with OFDM and like 5G channels or LTE channels, you know that the channel information, there's lots of frequency dependent stuff. Channels behave differently across, especially the broader bandwidth you have, the more weird it can get. So getting that channel information back quickly is really key. So classic massive MIMO problem. The prior work from this particular set of folks includes something called Lone Star, Steer, and Steer Plus. And so if you look up those things out there on the internet and archive and other places, you'll be able to see it. And so the question they had is how do we set up things without explicitly estimating the downlink and the uplink and the self-interference channels? Like we're talking about a lot of channel information that you have to find. So what do we do? We're going to implicitly estimate what we need to know from probes. Okay, so this is sort of like those pilot tones that you send out in OFDM. You're going to like send out little pings and you're going to get your channel information. So just like in OFDM, we have these, you have some number. They used tau as the variable for time slots in the front end of these super symbols. And that's where your beam learning happens. So you're gonna have little beam pairs. You're gonna figure out where your people are, and you need to learn that. So we're gonna do things like measure signal to noise ratio, your uplink, your downlink, the beam pair data, your interference to noise ratio, and your self interference. The thing that they are really trying to emphasize here is we don't need all of the channel information all the time. That's kind of the way it's done in a lot of specs and a lot of communication systems. We don't need all of this information all the time, just the parts that matter for our particular beams, aka customers. So the idea here is to be data driven, to not do all this work for the entire, airspace essentially, and then just extract the small amount of data that you need. So how do you do that? And I say, okay, you can design a probing beam pair from your first probe and then kind of repeat. So they're saying, be judicious about your resources to reduce the overhead of this beam learning thing, which can take up a lot of time and energy. You target the actual user pairs. They used long short-term memory models. These are sort of deep neural networks, LSTMs. They're used to learn what to do with the information that you're getting with this data-driven approach. However, these models, these deep neural networks, have to be trained on the full data. Okay, so you're not just training on these little tiny pairs. You're walking in with a fully trained LSTM model. And the big unknown at this point is the latency. That inferring your beam may still take too long for this to actually be deployed. And Ian Roberts at the Wireless Lab at UCLA, who's the person that gave this talk, and it had a lot to do with the stuff that we care about. There's at least two big areas of overlap in that, when we're looking at Neptune, um, this is what you just do. This is what you do in OFDM to try to get your physical layer to work. You send out these pilot tones, you get your channel information, you get the whole channel, you then make decisions on how to shape your signals. And LSTMs are what we are using in our artificial intelligence work. So when we do the work like with the RIDI project, it is an LSTM and it's a sequence to sequence AI/ML model. So that talk. The next one was quantization for optimal UAV. So this is like drones, network deployment. This was pretty neat. So just right off the bat said drones are very disruptive to communications, but this presentation kind of proposed a big reset and asked, is there a mathematical model from information theory that can deal with drones? 20 minutes was way too short of a talk. These are all 20-minute talks. The basic idea here is that you have to kind of think about drones as an antenna presence um, that is in 3 dimensions. Instead of your 2-dimensional map that you usually are dealing with for network theory, you now have a 3-dimensional map, and the edges, you have to account for the edges being kind of weird. So just think about it in 3D was basically the advice, and lots of really amazing graphs that looked pretty remarkable, and a few, I would say probably cherry picked, but a few examples showing that if you have a 2D approach to dealing with drones and communications to drones, that you're going to miss places where you really should have, made before break. You should really be either talking to a different drone or talking to a different ground station or dealing with interference that's coming from something that seems like it's either a lot closer to you or a lot farther away. And there was a couple of claims made here about you're always going to have a concave shell around a drone, that you're never going to have these intrusions where you have something like a shorter path. And I cocked an eyebrow at that because, especially at 5 gigahertz, there's reflections and weird stuff that happens with your channel. So that's one of the things that I wrote down. All right, and the next thing was pulse shaping filters and input output relation estimation and equalization in something called ZAC OTFS. Okay, so here's the abstract, and again, I'll pass these slides out later. But I was like, OTFS? What's that? I think I've seen the acronym before, but I was like, okay, now is the time to actually go and try to learn what OTFS is. It's orthogonal time frequency space. It's similar to OFDM. They're both methods of getting signals to spread across time and frequency. So our Neptune project is OFDM. We've been learning about OFDM and trying to implement it in an FPGA project and making some progress there. So a little bit familiar with OFDM now. But OTFS has some advantages over OFDM. So similar, The claimed advantages are better spectral efficiency, energy efficiency, and general robustness against synchronization errors. So, I mean, that gets lots of attention, from people. These are big claims. OTFS requires a smaller cyclic prefix and better energy efficiency. And how does it do all this? Is because you transmit your symbols in delay Doppler channels. So the constant channel measurements are not required. So again, here's another sort of presentation that's kind of trying to figure out how do we resolve some of the restrictions or some of the requirements from things like OFDM. So what's a cyclic prefix? Well, there's a really good explanation in Wikipedia. The cyclic prefix provides a guard interval to eliminate intersymbol interference. So you're chucking your values out of your antenna, and in between your symbols, you put in a little prefix. You put in some extra data. But it's not just any data. Just any data would give you guard time. But wait, there's more with especially like OFDM. If you take the end of your symbol or the beginning, doesn't matter, as the cyclic prefix, then you turn a linear convolution into a circular one. And in math, this makes everything so much easier. So your cyclic prefix is not just there to make the intersymbol interference better. Your cyclic prefix is there to do some cool math stuff. And shorter cyclic prefixes, oh yeah, that's actually a big win. So that got my attention. And then delay Doppler channel. I'm like, I don't know. This stuff's hard. Like, okay, now you're gonna throw a delay Doppler channel at me. Okay, so it's a channel where the signals have time delays and Doppler shifts. So if you imagine your resource grid from OFDM, one axis is going to be your time delay, and the other axis is your Doppler shift. So like, okay, you can set it up like a 2D visualization, delay and Doppler. And radar people deal with this a lot. So if you're a radar person, you're going like, yeah, I get it. If you're not a radar person, then you have to kind of like wrap your mind around it a little bit. Analyzing both of these factors at the same time, assuming that you have both of these in your channel, gives you a lot better performance in many ways. And so that's why OTFS is being considered for 6G, because it avoids this constant channel estimation requirement that OFDM has. The heart of this talk, is about the shaping filters, because it turns out that the pulse shaping filter that you put on your symbols when you chuck them out the door it makes a difference. Gaussian doesn't really work terribly well, and sync doesn't work terribly well. So the speaker said, hey, why don't we split the difference and we create a combined Gaussian sync filter, and they called it a GS filter. And then they ran it through all sorts of Simulink and MATLAB and showed that it actually does kind of help. It's a compromise filter. And this caught a lot of attention from the room, especially from digital communications people who were a little flustered about this. And asked lots of tough questions, but it sparked a lot of conversation, and at least in simulation looked like it worked. Okay, last one. This was error correction in interference limited wireless systems. Okay, so we're talking about wireless systems where the interference is harsh. And basically, what do you do? Okay, so again, this is the abstract, very dense. Basic idea. So this is like an IRC channel own, when you take over the channel. Oh, you've got noise? I can remove it. The basic idea, you've got the ability to sample the channel often and with enough resolution that you can simply subtract the noise or interference from the received signal. And you're going to get that signal back. And it's like, wow, why don't we do this all the time? Well, because it only works under certain conditions. And if you have high signal to noise ratio and kind of a low interference noise ratio, just use your classical detection stuff that's going to work as good or better. If you have decent SNR and high interference noise ratio, that's the best case. You can sample and subtract the interference from the signal. You get a much cleaner signal. It gives you results really quickly with low latency. The worst case where this doesn't work for you is when you have kind of equal signal to noise and interference to noise ratios. If you have high interference noise ratio, then you can just subtract that interference and not and then you can deal with the noise. So that was something that I think that in an age where we have access to fast processors, lots and lots of digital signal processing, where we have increasingly larger and larger FPGAs, these sorts of techniques actually become achievable, like practical, um, not without some work. But the balance that a lot of us have seen in our working lives and in our uh, kind of explorations through coding and engineering are a balance between, okay, just brute force it versus a very clever algorithm. So sometimes the clever algorithm gives you a lot of traction, and sometimes the right solution is simply to brute force it. And so to me, this was like, hey, just brute force it, just sample the living daylights out of the channel, and you're going to be able to recover a signal. Okay, so that was day one. I'm going to stop sharing. And I thank you all for hanging with me here for a little bit extra time to kind of go over some of the stuff that we learned about from ITA. Um, so I don't know. Some of this is actionable stuff. It kind of informs the projects, and some of it is much further away. I have some additional content from the second day and the third day, and I'll introduce that over the next couple of weeks, and uh, and try to backfill the slide deck with a little more, maybe some diagrams from the slide decks from the presenters. There's some papers that I'm going to go try to read, and I'll try to bring that back to the group and fill it in. So any questions or comments about any of that?
Are those, can you make these slides available somewhere? I'd like to maybe sit with them a little bit.
Yes, absolutely. I know that I tried. I'm going to keep put the whole abstract in there, and then I'm going to try to go get the actual original slide decks from the presenter. So yes, all of these slide decks will be in our repo very shortly.
Yeah, interesting stuff. Were any of those presentations recorded or would be published?
Unfortunately, no. The some years the show or the workshop has had like an AV crew in there. But I can't find any evidence of any of these presentations ever being published. And I've been going since for more than a decade. So no, since it's an informal workshop, um, and it is definitely it's got an informal vibe. It does. Like the presentations get moved around and the schedule is just kind of advisory. But no, the talks are generally not recorded.
Hmm, okay.
Yeah, it's a
Sounds
really
like an
fun
interesting
group.
workshop.
No, it is in the information theory kind of community. It's one of the more well attended annual events that's been going on for 15, 16, at least 15 years. And that there is another information theory like conference that's a little more formal where the stuff's more polished and you get like the more traditional sort of IEEE sort of conference. But if you want to go see like a more, I would say more like diverse or interdisciplinary set of presentations in a more relaxed environment than ITA in San Diego, almost always the week of President's Day or Valentine's Day week is when it's always at. That's the one to put on a calendar to go see. Lots of wireless and digital communications content, and a huge uptick in information theory applications in artificial intelligence to large language models, machine learning, deep learning. There's a lot of activity there in those categories. There's still an awful lot of, polar code, LDPC, forward error correction, compression, encryption, that sort of thing. And then applications they vary from biomedical to indexing viruses and how to get them properly, you know, recorded and represented, um, to what I'll talk about next time we meet is an interesting hardware vulnerability, a hardware hack, which has some sort of information theory base, the basic idea of the hack. I'm calling it a hack. They presented it as a vulnerability, cybersecurity sort of issue. Is that if you can modify the coefficients for the shaping filter, for your transmit filter, like a sync filter or whatever, if you can change that, then you can have a covert channel. Now, this assumes that you also have some way to get information in and also orthogonal to your main signal, and you're going to have to settle for a much smaller data rate. But that's a team of folks working at the University of Texas, Dallas, I think, and they're they've got like this is pretty cool. It's like, oh, this makes total sense as a covert channel that could be in hardware, that you could take advantage of chips, communication chips, and all you got to do is kind of change that filter shape. And we do in manufacturing allow for a lot of leeway here. So, when we have a filter mask or a set of specifications for devices, we're leaving a lot of room there for the filter, the final filter, to have extra lobes or extra energy in lobes, because we have to account for things like manufacturing variation, for temperature, for aging, drift, those sorts of things, multi-band, lots of reasons to have extra space in the filtering. And it really isn't isn't much of a bigger step, to then say, oh, okay, well, now you can put information there. So that was one of the talks that I'll go into next time we meet.
It's very interesting. Yeah, thank you.
Oh, sure. Now, I think over the next week, we're looking forward to celebrating National Engineers Week this week. So we will be at an event, awards banquet tonight, and that will. So it's the San Diego County Engineering Council. It's having a big shindig, and we'll be there, kind of representing open source digital hardware stuff. So this is a kind of a fun week for us here in San Diego and around the country, as different places are celebrating it. So looking forward to that. Yeah, so it'll be a good week. I think kind of a highlight of the year is to go and celebrate with all of the other many industry and academic organizations. IEEE is a big part of this council, along with a huge variety of other folks. So looking forward to that. Be able to report back on all the fun things that we get to experience. All right. Anybody else have anything to share? Would like to report? We also have done some work on a link budget for Earth, Venus, Earth project from that we learned about it from Deep Space Exploration Society. And that the first draft of the modified link budget, we took Jan King's DVB-S2 Geo HEO link budget for 10 and 24 gig, and we're using that as a base, and we're going to modify that link budget for Earth, Venus, Earth. So if you're familiar with Earth, Moon, Earth, or EME, this is bouncing signals off of Venus instead of bouncing signals off of the Moon, to be picked back up. So this is sort of reflect the signals off of a planet, another planet. Very exciting. So we're doing as best a job we can to work through the link budget on that and come up with some solutions for how to structure the signal. So there's been at least one meeting, and I think tomorrow will be the next meeting of the planning group. And I think Matthew's going to represent us there. So plenty going on with interstellar link budgets. Okay, well, thank you, everybody. Especially thank you for staying after to listen to the roundup from day one of ITA. And I'll make sure to distribute those slides and have the other talks ready to go the next time we meet.
Hey, thanks for having me.
Oh, sure.
And,
Thank you so much
yeah.
for hanging out with us. It was good. We'll see you next time.
Yeah, sounds good.
All right,
All right.
everybody. All right, see you soon.